Hello everyone, in this video I'll be explaining about the non-ferrous metal separator, otherwise known as the eddy current separator. Before we begin, let's talk about two different types of metals, ferrous metals and non-ferrous metals. So we shall start with ferrous metals. These contain iron, also known as ferrite. They are more vulnerable to rust due to the higher carbon content and are more durable. They also have magnetic properties, which basically means they can be attracted by magnets. Some examples of ferrous metals are stainless steel and carbon steel. Moving on to non-ferrous metals, these don't contain iron compared to ferrous metals. They are higher and more malleable and have a higher resistance to corrosion. Most importantly, it does not have any magnetic properties, which means they will not be attracted by magnets. Some examples of non-ferrous metals include aluminium and copper. There are few laws and concepts that must be understood before learning about how the non-ferrous metal works, one of which is electromagnetic induction. This is the process when current is induced because of a change in magnetic field, which could be caused by the motion of a conductor across a magnetic field. There are two laws that is closely tied to it, which is Faraday's law and Lenz's law. Firstly, Faraday's law says that an electromotive force or an EMF is induced if there is a change in magnetic flux, and the EMF is directly proportional to how fast the magnetic flux is changing. The way that Michael Faraday obtained this law is by doing an experiment involving a galvanometer, which is used to measure current in a solenoid, which is essentially a coil of wire and a permanent magnet. He attached the galvanometer to the solenoid as shown in the image and started his experiment. And these were his findings. When the magnet is stationary, be it outside the solenoid or in the solenoid, there is no current flowing, hence no deflection on the galvanometer. When the magnet is brought closer to the solenoid, at the moment when the magnet is brought closer to the solenoid, with the north pole towards the solenoid, there is a deflection on the galvanometer to the right. At the moment when the magnet is brought away from the solenoid, with the north pole still towards the solenoid, there is a deflection on the galvanometer to the left. The first thing to note is the results, which will be reversed if the south pole of the magnet is pointing to the solenoid instead of the north. And the second thing is, the quicker the motion of the magnet, the larger the deflection on the galvanometer. Moving on to the second law, which is Lenz's law. Lenz's law says that any induced EMF will always produce a current which has a magnetic field that opposes the original magnetic field that causes it. Lenz's law states that induced current always flows in such a direction which opposes the change causing it. Now the diagram here is I'll show the examples here. So for the first one, we have a solenoid which is caught with a wire right here. And left, we have a permanent magnet, and we'll put here as north pole here, and here is south pole here. And the solenoid is right here. So we move the magnet towards the solenoid. So the north pole is here, and the South Pole is here. So the motion, the change, which is also the motion, is in this direction. So based on the Lenz's law, the induced current flows in such direction which opposes the change, or we can say the motion causing it. In this case, the change in motion is the change of the motion of the magnet. So what we have to do is, the opposite change is, we know the North Pole is here. So the induced current must act in a way that so that it causes this side to be the North Pole. We know that same pole, they repel. So it will oppose the motion causing it. So applying the right-hand grip rule, if you still remember it, right-hand grip rule shows that this is the North Pole. So how does this current flow? It flows like this. So the direction will be here. So in this case, this side of the solenoid will act as the North Pole. That's why it will repel the motion causing it. So it's the same thing we do for the next one. Here's the north and here's the south. Same towards the solenoid. So opposes the motion causing it. So at this side, what should it be? We need to repel the magnets. So at this side will be a temporary South Pole. So how should we make this solenoid a South Pole at this point? So applying the right-hand grip rule, it flows in this direction. So the current will flow in this direction. It flows in direction the South Pole. Next, North Pole and South Pole of a magnet in this direction. So we move the magnet away from the solenoid. So we need to know that it opposes the change in causing it. So when it's away from the solenoid, we need to oppose the motion. So you need to pull it back. So it has to be here, South Pole, so that it opposes the direction of motion. So the induced current will be in this direction. The induced current will flow in this direction. Next, here we have North Pole and South Pole in this direction. It will pull the magnet away from the solenoid. So we have to have a temporary North Pole at this point, so that it will oppose the change which is away from the solenoid, causing it. So this point should be north. So how should we induce current flows so that this point is a North Pole? We apply the right-hand grip rule once again. So in this direction, this is how the induced current will flow. So we hope you understand this. So basically, Lenz's law is a form of the law of conservation of energy. So we can see that there's an opposing force occurring here. We have to oppose the motion. So a work done must be done to overcome the opposing force. So the work done to oppose the force is converted into electrical energy, which creates a induced current. This is why we can say that Lenz's law is a form of law of conservation of energy. So that's it. Thank you. Last but not least, eddy currents. These are the currents that were induced in conductors due to a changing magnetic field. The shape of eddy current is shown in the picture. It always flows in closed loops and are perpendicular to the magnetic field. The magnitude of this eddy current are proportional to the strength of the magnetic field, the area of the loop, and the rate of change of magnetic flux. Here we have a strong permanent magnet on top of a pure copper plate. Copper is a non-ferrous metal which does not have any magnetic properties, which basically means the copper will not be attracted by the magnet. What the magnet induces in the copper is the eddy current, which resists the magnet from falling like a normal object. It will slow itself down when it is just above to reach the copper plate. But why does this happen? When magnetic field of the magnet intersects with the conductor, which in this case the copper plate, eddy current is induced in it, and this current induces a magnetic field which opposes the original magnetic field by the magnet as per Lenz's law.
Finally, moving on to the non-ferrous metal separator. This is used to separate the three different types of waste, which are ferrous metals, non-ferrous metals, and non-metallic waste, such as wood, glass, and plastic. Alright, so this is a diagram of the non-ferrous metal separator. As you can see, there are two parts of the separator. The first part is used to separate the ferrous metal from the other waste, such as non-ferrous metals and non-metallic waste. After the ferrous metals have been removed, we move on to the second part of the separator, which is separating the non-ferrous metals from the non-metallic waste. Okay, so let us explain the working principle of the non-ferrous metal separator. For the first part, the ferrous metal will first be removed using a strong electromagnet, because they are the only type of waste that will be attracted by the magnet. These ferrous metals must first be removed, otherwise it will become hot inside the eddy current field, which might damage the conveyor belt. Then, the non-ferrous metals and non-metallic waste will be left at the conveyor belt. At the end of the conveyor belt, there will be a rapidly rotating magnetic inductive cylinder, which is composed of a large number of alternating magnetic poles, which is called the magnetic rotor. The magnetic rotor are rapidly changing magnetic field, which generates eddy currents in the non-ferrous metals. These eddy currents give rise to a magnetic field that opposes the original magnetic field causing it. In this case, the magnetic rotor. The effect of this is that the non-ferrous metals are ejected across the splitter into a collecting beam. Last but not least, the non-metallic waste like plastic will not be attracted by the magnet, nor will it be induced with eddy currents. So it will just go down the conveyor belt and free fall downwards towards a separate collecting beam. At the very end, this is what it will look like.
Four neoflux magnets create an extremely intense magnetic field. In this way, the eddy current separator not only separates the big particles, but it can also separate the smaller ones, the smallest particles being those of ½ an inch. The adjustable angle setting of the magnet rotor makes the eddy current separator suitable for almost all materials. The separation coverage for the valuable particles is horizontally and vertically adjustable. This way it is easy to achieve the best possible separation. The eddy current separator is built according to the eccentric magnet rotor principle. This technique prevents the weld penetration of the iron particles on the magnet rotor.
Additional modification done to a non-ferrous metal separator is making the splitter for non-ferrous metals and non-metallic objects adjustable. This allows for the most efficient separation. Next, a vibrating conveyor belt. This allows for a uniform distribution of materials. Third, the different separation of system for ferrous metals and non-ferrous metals. This is to minimize the wear and tear of the conveyor belt. And lastly, the liquid cooling system for the separator. This works by having a pipe filled with water flow through the separator, effectively carrying away the heat being generated.